So that is why I start 5-10 minutes in advance just to introduce rotations. Okay. Another 5 minutes. Okay, I will say something more. Semi-simple group, don't worry if I mean if it is not clear, I will give an example and then start with that. And another thing is possibly one of the speaker here will talk about Savali groups. I think Pradeep Shukla, Ravindra Shukla will talk about Savali groups corresponding to the but anyway, I will give one example for everything, whatever I am going to do today. So that will be clear, so that it is not that completely bad. So I say A because there are finitely many. Given a G, there are finitely many. Let us not get into that, but one example is fine. again here I mean there is a contours correspondence and so, W prime I just say normalizer of T, all those elements which by the conjugation it should T the points of T, not the points of T individually, the set is fixed, it is not changed, and W prime the quotient group normalizer mod T, and this I will say why this is, I mean not the proof, but what is the connection, why, I mean what is the connection, why that not the proof, but the idea why that is equal to W that is being already talked about. So, here the one thing, and I have this G to GLG adjoint representation. And we have the CG, this is the polynomial. Functions on G. Thing. Okay, so just before making any statement, I just give the example, just one example quickly. This is the determinant. Okay, so I think I don't give all the all the things in the example, but whatever is most important. I mean the group, full group, torus, Cartan subalgebra, Borel subalgebra, Borel subgroup, the Weil group, normalizer, everything is more or less given. So let me now say what I am going to lecture on these three days. Things are relevant to the Chevallier's theorem, then the Harichandra's theorem, then there are formulas giving characters for various representations of the entire semi-simple Lie algebra, also the multiplicity of given weights. So, that is due to Constant and Hermann Weyl, and also the Freudenthal's formula and then Steinberg's formula. But mostly I will concentrate on Chevallier's theorem, Harichandra's theorem, Constant's formula and Hermann Weyl's formula. But other things, Freudenthal and Steinberg, I just state them, but I don't concentrate due to time constraint. Also one more thing, it's I should thank the organizers to recall study of the Chevallier's theorem and Harichandra's theorem, and also the Constant formula. I am just trying to understand some of the things that where I am interested. So that way. Okay, so the first thing is Chevallier's theorem. What is the thing that? So take any polynomial function theta, restrict to CH. It's a restriction function. So any polynomial restrict to f to h. Now, if I take any polynomial which is invariant for G, I would have mentioned a few things here. One is that the action of the adjoint representation, the SL and C, acting on little SL and C, is the conjugation action. The conjugation. You can see that if we take a determinant 1 matrix, take a trace 0 matrix, the Gx G inverse is again a trace 0 matrix. So that is the action in our special case. And on the diagonal matrix whose trace sum is 0, the permutation action is simply permuting the coordinates. So sigma of that is x sigma 1 s sigma m. So this is the action. Yeah. So this is the action I am talking about this side, and this action I am talking about that side. So now if I take f of this thing, I claim that f restricted to h belongs to CH upper W. Let me just have a quick reason why this is true, because f by definition is add of so let me take any W here and any x in H, then f of W times x is by definition f of add n times x, where n is an element of the normalizer whose representative is W. See, by definition W is the quotient of n by t. Because t is abelian, t the adjoint action on H is trivial, because abelian think intuitively is conjugation action, and the abelian level conjugation is trivial. Therefore, t action is trivial on the H. Therefore, n mod t will act, because t is in the kernel. So, the Weil group will act on that. So, this is precisely n of that, where n t the representative is W, right. But you see f is coming from invariant here. Therefore, this is simply f of x. So, therefore, the restriction is W invariant, that part. So, now this is the beginning of the theorem now. So, let me state the theorem now. map theta this is the first thing G to H W is an isomorphism. To polynomial algebra. But what is important is we are going to concentrate again only on this. The reason is the first part is more important for us. The second part is also important in the general theory, but for our purpose of this workshop and what I am given as this thing, second is not relevant, but as a statement just 1 minute to take, that is why I state that. It is important to know that it is a polynomial algebra. Pure polynomial means there are no, it is a finitely generated algebra, but there in general there may be relations, but here it is a polynomial. Okay, so we are going to concentrate on this part. So, proof of 1. So, first thing is the step 1. So, today's thing mostly I will concentrate on the proof of 1 and give the example of the SLN case on the right side. It is CH of W. It is a very well known thing due to Newton that I will explain. These are the two things I am going to do today. I mean how this is a polynomial ring I will explain. For the case of W is the symmetric group and H is the diagonal matrices whose sum is the trace is 0. So, here the first thing is theta. I mean this map is theta. Theta. The kernel of theta is 0. That is theta is 1 to 1. Of course, it is clear that this respects this restriction from a vector space to another subspace is clearly a homomorphism of C algebras. It is clear. So, this map is clearly a homomorphism of C algebras. There is no problem for that. And first thing is, therefore, we have to check only two things. One is that theta is 1 to 1, the other one is theta is on 2. The first step is to, okay. So, why is that? So, let us take here I will explain what that I am going to use, and we will, if we need some of these things we can do it in the tutorial. Means if some explanation is needed for certain statements, already I have prepared some things for tutorials to do some things. Apart from that, if there is anything that if you think something is needed to be done, I am willing to do that. Okay? I mean, but I will state the statements first. So, the set of all semi-simple elements of G is dense Zariski dense subset of U to G. So, use the adjoint representation, and here you have the Jordan-Chevalier decomposition, okay, xs plus xn, and the element is semi-simple if x equal to xs. So, what we mean by is diagonalized, that is what, that is the medium. And because it is injected, there are no center here, I mean semi-simple. So, that the element is well defined, I mean the semi-simple city is well defined. So, we can talk about semi-simple elements. Here, the set of all semi-simple elements is Zariski dense. If it is not done so far, I would like to do in the tutorial. If it is not done, I mean I do not want to redo it, but if it is not done so far in this workshop, I will redo it. I will do it. I am willing to do that. Okay. So, can I rub this part of the board, this notations? Can I? Yeah. So, we use that densities to prove the. Okay, so now let be in the kernel of theta. Now let x be any semi simple element of now, there is a Cartan subalgebra H of G such that x belongs to H. This theorem, I think it is proved already, or can I assume it is proved already? Oh, not, but there is a possibility of proving in the
stating.
Huh?
Stating it.
Yeah. So, what I mean is I do not have to, should I have to do it in the tutorial, or that can be done? Okay, fine. So, he is saying that this theorem, this is a theorem which will be proved later. I assume that theorem.
You can feel free to discuss it.
Yeah. So, some things I assume and whatever is, yeah. So, there is a Cartan subalgebra H. Okay. I am again going to use another theorem also, which, okay, so theorem 1, theorem 2, there is of course, this theorem would have been proved already, would have been, because there is no notion of Chevalier group already, therefore. Pardon?
We have already fixed the Cartan subalgebra H.
Already?
Fixed already on the Cartan subalgebra. H is already fixed.
H is fixed, yeah.
This H may be different.
H prime, sorry, this is H prime, sorry, not that H prime, yeah, you are right, very good. So, it is H prime, not that H, may not be that, it may be that H, but not necessarily that H, correct. So, there is a H prime, yes, correct. Theorem, there is a G in G such that add G of H prime equal to H. Okay. Like any two maximal tori in a conjugate, any two Cartan subalgebra is conjugate by a limit of G. Now, which means, so this theorem also I think will be proved later, which means add G of x is in H, because x is in H prime, add G of x in H. Now, what about f on x? This is same as f of add G of x, because f is G invariant. We are in the kernel of that thing, f is in this thing. So, this is by definition, this is already invariant. Okay. So, f of x which is equal to this. Therefore, this is same as, but you see this add G of x is inside H. Any question? Add G of x is inside H, Now, I am in kernel of theta, therefore, f is identically 0 on H, because we are looking at the restriction. So, this is 0. 0 since add g of x belongs to H, and of course, f is in kernel theta. Okay. So, what we have shown is that f is identically 0 on the set of all semi-simple elements of G. But now, the first I think this is the this even the theorem 0 or whatever. So, or the exercise that set of all semi-simple elements is a dense subset of this. Therefore, this implies f is a polynomial. So, this is identically 0, because Zariski dense means the closer in the Zariski sense should be the whole of that, but Zariski means it is given by polynomial conditions. So, that means f is identically 0. So, which means which implies kernel theta is 0. So, we are done with the step 1. Yeah. Step 2, we have to use the something more about also the dominant ordering and other things. Okay. Step 2 is theta is on 2, but we have partial steps for this thing. So, partial step 1. First thing is let lambda be a dominant integral weight, then V lambda irreducible representation of G with highest weight lambda. This was done by Anupam Kumar Singh in this workshop. So, here look at this row from G to LV lambda, the representation map. Then this so, the thing is V lambda is a finite dimensional representation, because it is dominant and integral. It is not true for every linear form, but if it is dominant and integral, then V lambda is a finite dimensional representation. So, I could very well talk about trace. Okay. So, trace of rho. So, the map x to sending trace of rho x to the power k, any non-negativity here is a G invariant polynomial function. A small work need to be done, why there is a polynomial, but I leave it that. But it is G invariant because had and then that because it is comes from that, I could use the simplistic connected cover and go from that group to this. That representation actually comes from the group, the simply connected group. So, and then the image will be the conjugation. So, it is exactly conjugation. The image, what I mean is rho of G of x is something like rho 1 of G rho of x, rho 1 of G inverse, something like this, where rho 1 is the representation coming from the group. Okay, this slips there. So, but this is when you do the trace, this trace is invariant under the conjugation, therefore, this map is an invariant polynomial. Okay. Now, this one fact, partial step 1 is that this is done. Partial step 2, I just defined the define. Okay, partial step 2 is some exercise. I leave that exercise. So, this is CH is a polynomial algebra on H, okay. But you see there are linear forms already here, therefore, already this is also there, this is also there, and all those powers are also there, because this is a symmetric algebra of H star. So, all the powers are also there. Okay. So, as a C vector space, this is a this CH is a vector, as a vector space is spanned by this lambda power k, lambda is in lambda and k non-negative integers. First what one can do is, this I will do, this I will do in the I will do it in the tutorial. So, let us not discuss about it now, just assume and then get into the proof. Maybe I am going fast or okay. Should I reduce the speed? It is not clear, I can explain again. I mean, if I have time, if I complete early, if I have time, before that I can do one of the exercise even in the, if I have time, okay, otherwise. I do not want to talk about the next Harishchandra theorem today. I want to only concentrate on this today. Okay, so how do I use this to prove? Yeah, the step partial. So partial step 3. This is one, just one statement. So let lambda be any, or let mu be any integral weight, then there is an element of the while group such that now we have integral. This is already proved, just I think it is already proved. Given any weight, there is an element of the while group which takes that weight into the dominant weights, dominant chamber. Okay? So, I am just stating, I need this to use, I am going slowly, so that the idea will be very clear. So, what is partial step 4? W mu. W mu is lambda. Yes, W mu is lambda. I want lambda to be in the dominant chamber. That's why I start with mu and then I ignore lambda. Okay, so W mu is lambda. I want always lambda to be in. Okay, correct. W mu equal to lambda. So, partial step is 4 is that if I make some mistakes like this, please feel free to say that. So, now, now the whole point is to use this. What are the Weyl group invariants here? Okay. So, now I take this is a notation sim lambda. So, lambda be a dominant weight, sim lambda equal to sigma this is the orbit sum. Sum of lambda is the orbit sum. Now, it could be repeated, but we are in C, therefore, there is no problem. It will be non-zero always. I mean, no, this may not be. This may be 0 because there are no invariants, but now the for okay, non-negative take some lambda power k to be maybe you could see that this is 0 already. This is 0 is one can see because the representation h or h star, it is irreducible. So, that it cannot have invariant because otherwise there is an one dimensional representation which is a sub of that. So, this is not possible. This is always 0, it is 0. But then, I mean, as this thing I have to put all of them together. But powers are not okay. Fine. Now, the thing is, this is the partial step 4. What is the thing? The Klein. Clearly, that these things are in CH and they are all invariants, there is no problem. This is no problem. But the thing is that this generate, this is the thing. That is where I need that this thing is generated by this thing. This is what I am going to use. So, let us take any f in CH upper W. So, f is so f will be of the form sigma a mu k lambda mu power k. So, mu is in the lambda and k is in non-negative integer and of course, A mu k's are the complex numbers by step 2, partial step 2. Okay, so this is invariant, but now you see I start with the W invariant. Okay, let me explain a small little thing. You take 1 mu k for mu power k for which this is coefficient is non-zero. See, if it is 0, we don't worry about it. So, if it is non-zero, then because of the W invariance, for every W mu power k, I mean for every W mu power k is also having same coefficient. So, what I am saying is for every k non-negative and for every mu, A mu k is equal to A W mu k, and for every W in W. Of course, I would have written here for every W in W. This is okay because of the W invariance. So, but you see, by one of the other partial steps, the step 3.
The statement is that you can choose A lambda mu k such that that holds.
Right.
See, F could be, there could be several expressions like that. And you are saying
Linearly independent.
so since they are not, could they be,
mu power k is
you can choose by just again writing
Yeah, yeah.
averaging W. So
Yeah.
you can choose. So what the statement at least is that what you're saying? You can choose the expression such that this condition holds.
yeah, you suppose mu power k appears twice or mu power k, you mean to say that mu power k and a W mu power k should be the same? Are you talking about that or are the?
Yes, for that.
Yeah.
So the expression need not be unique, I assume, or is that?
The expression A mu k to the power b, times mu power k. So the linear dependency. Yeah, but that's okay. Even if it is not linearly independent, you can always. There is not a problem. I haven't checked whether there is linearly independent or not, but it is not a problem. I mean, you can always.
You can assume that the expression
So whatever is involved here, you can ignore the things, the relations, and then because we are talking about only the generators, not the linearly independency. So so that way you can take those things. But finally, this is unaffected by whatever is after relations also, whatever revived, that W of that will be there. Okay. Now, this I can take F to be, therefore, F is also of the form sigma. But given a mu, there is always an element of the while group for which W mu is dominant. So, there is always a nice one in every mu power k. So, I could write this as sigma j lambda k lambda power k sim lambda power k. This is, and then k comma lambda in dominant and k is a non-negative. So, this is what I want. So, because that A lambda k is same as A W lambda k, therefore, W of lambda power k will have same coefficient. So, I can take the sim by dimension is the sum of things. So, I can okay. Now, therefore, we have shown this one that sim lambda power k generates this thing. Okay, so now I use this to prove the surjection. So what remains to prove is therefore the step partial step five. What remains to prove is that because theta is a linear map. So, if the image contains a generating set, then we are through. Okay, that is already. So, this is what. So, it is sufficient. So, to prove this is the last step. So, but we have already told some of these things like partial step 1. Okay. So, now coming back to the partial step 1, from there let us consider this trace of rho x to the power k. So, fix rho lambda, fix lambda dominant and fix k also positive integer. So, let us look at this trace, yeah, and consider theta of that. So, that belongs to C of h upper W. So, what is that? So, that let x be in H. Now, we have this map G to GLB of lambda. So, this is a representation and H is of course here. I just make a statement, tell me if it is proved or not proved, that this is semi-simple or completely. So, what I am saying is no, this is diagonalism. That is proved already, right?
Proved exactly, but stated.
Oh, stated. Okay. Okay. Whatever. I mean, okay. I'm not. So what I mean is, okay. I can use that. That's what I want. I don't want the proof, but I can use this. Okay. Pardon?
You have to use that sim operator, the 1 by mod W, that average. So if you apply that to 1 by mod W sim of f, that will be again f.
Yeah. Yeah.
So f equal to 1 by mod W sim f. So that will go inside. So then, so So that will be summation A mu k, that one mod W, sim mu k. But sim mu k is same as sim W mu k for any W.
Yeah.
So we can collect all those, then collect all coefficients. So then we can make F equal to that.
Yeah. Yeah.
So if we just apply one W, then we can't conclude it. We have
Sim
to
is,
apply that one.
sim is over all little w in
Yeah,
capital.
okay, it's just summing. We have to average that. One.
Yeah, 1 by order of the
One by
isotropy. You are talking about isotropy. Okay. I mean to kill the see, because we are in complex numbers, so that will be if that is non-zero, then it is also non-zero.
F equal to 1 by mod W sim F, because F is just W invariant. So WF equal to F for all W.
Yeah.
So sim F is nothing but mod W into F.
Oh, you want to make 1 by W there? Oh, you want to make here 1 by W? That's okay. That's not a serious thing. You can. But 1 by W that generates, that also generates.
This is not a basis, so we can't directly conclude that. If you apply some W, then
Anyway, we will discuss in the tutorial. I don't understand what you are saying. We will discuss in the tutorial. Okay. Okay. So this rho lambda of H is diagonalizable. This then now here. So this is diagonalizable. Therefore, the trace of rho lambda of x to the power k. So fixing a, so we have already fixed an x here. So this is simply the sum of sum of kth powers of the diagonal I mean of the eigen just we have diagonalized, so that will be of the form some alpha, some a1, a2, some an. This thing could be repeated also. Okay. But here there is one nice thing with lambda of x power k appearing exactly once. No, what I mean is it could be repeated. I am not. No. What I mean is that lambda as a linear form. Okay, the question may be is probably confusing that lambda x. So w lambda could be lambda for a w different from my entity. I am not talking about that number. Okay, I mean what I mean is lambda as a weight. I am not talking about the value lambda x. That could be with some number. Okay, that is always true. I mean, because the isotropy is there, I am not. But as a weight, that lambda appears uniquely. That's all I am saying. For example, in some cases, of course, minuscule. I mean, there are many cases where the w fixes this thing. But that is not going to bother. What I mean is, as a linear form, that lambda, okay. Of course, w lambda also as a linear form could be same, but I am saying in the thing there is a unique highest weight of weight lambda. Okay, but does not matter, you put an integer, that is not going to bother me again, even if there is an integer also, positive integer, because there is anyway we are working with complex numbers, so we should not bother too much about the isotropy and such thing, because p, there is no p annihilating characteristic, p is not coming. So, we should not bother too much. So, by this I mean, okay, maybe I should, if you want to make it with A for some appearing with some positive integer A. Okay. Now, it will be very precise. Okay, let us not. So, A will be there. Okay, so now the and not only that, and the and for any and a coefficient of mu x to the power k is non-zero in K implies, just you are able to read, or okay, so implies mu dominant implies mu lambda minus mu is equal to sigma mi alpha I equal to 1 to n for some choice of non-negative integers mi. So, what I am saying is, if you take another dominant weight, see, this is a sum of certain eigenvalues. I mean, I am talking about as functions, even though I fix x, I am talking about as linear forms on H, entire H. It will be like, I mean, this finite dimensional irreducible thing, it would have been mentioned that you look at this weight, I will recall this notation, no? Phi lambda, the set of all weights of the irreducible. So, this is set of all weights of P lambda. So, that means you have that is that so there is a mu, so weight means mu belongs to this means lambda times this h x times this is mu of x times v for every x in h. This is the meaning of mu being a weight. Of course, v is non-zero. So, v is 0 is always there. So, here if you take any dominant weight here, then that should satisfy the condition that lambda minus mu is a non-negative integral linear combination of simple roots. For example, that's how one can prove the set of all weights of V lambda. I mean, if you ignore that V lambda is a finite dimensional, still you can prove that set of all weights is less than. This is the way I mean combinatorially without looking at representations. Okay, that is there. Because there are how many, given a dominant weight, how many dominant weights are below? Not too many. Because at some point, if you keep subtracting simple roots, you could go negative. So, this way. Okay. So this statement tells you that this one, so I use the other word, that this will be So now the this one rho lambda power k. I use this notation. That means of any x is trace of that. Okay, this is equal to if I use this notation, I don't have to put a. That's why there is no w. I am not dividing because a is also coming. That is why I prefer to use this notation. So this one plus sigma a mu mu power k and mu dominant mu external lambda. Restrict to here I am using that V lambda has multiplicity 1 and all extremal weights are included here, even if the weight is different equal. W lambda equal also is included here. So this one is there, right? I used this part, and I think I don't know if the beginning. Yeah, this means sim. Yeah, here there is a sim mu power k. Sim mu power k, mu is less than or equal to lambda. Yeah, this means mu. This meaning is lambda minus mu is sum of for all I equal to 1 to n. So this one is there. Now here I am just coming closer to the proof now that theta is on 2. Now look at this part. This is already in the image. Definition is an element there. This by induction on this ordering. Okay, so the proof is therefore the proof is by induction.
The other one is true by induction and the left hand side. You mean the left hand side is already.
Yeah, left hand side is already there, therefore that one is also there. Yeah. So proof is by induction on this ordering. So now this is already by induction, this is by the definition, this is in theta. Cg, theta of Cg. Because by definition that I wrote partial step 1. Partial step 1 was the map x going to trace rho lambda x to the power k is a G, capital G invariant polynomial function on the Lie algebra G. So this is already coming from the image, theta. So this restricted to H is in there. Okay. Now, okay, so let me not write here. So this by induction. This is by induction. This is by induction. Therefore, this one comes from. See, this is already in the image because it's coming from trace of some representation. Not it's in that sense it's a genuine. It comes from a representation, so it's a genuine W invariant. Of course, finally everything is a genuine. All W invariants are genuine. Okay, but this is actually coming from a representation, not just a formal sum. We are not just cheating by writing something. Okay, but finally it happens that this is a genuine thing. This by the induction on the dominant ordering is Okay. So, here only one small one question is that what do I mean by so if I start with the minimal, I mean there is nothing, then it is the nothing is here. So, this is already equal to this. So, then I mean this is already genuine, therefore, so we do not have to bother in that case. So, the minimal things, okay. Maybe if time is there in the tutorial, we can do some minimal examples of minimals for just for curiosity. Minimal examples in the, I mean if the time is there, we can do in the tutorial exercise. Minimal examples, minimal dominant weights. In the case of SLN. There are very nice examples. These things, I will do that. Soon I will do that. Okay, so proof is complete, right? Mu is dominant. Less than, strictly less than. Yeah, of course. The lambda is not there strictly. Yeah. Lambda. That's why I put lambda already here. Yeah, it is. That's why I mentioned that the multiplicity is unique. I mean, I keep mentioning it, but when I write, okay. Yeah, you are right. So strictly less than. Yes. Otherwise, no point in I can put. Yeah. The point is that V lambda. Again, I mean, I have told everything, but what I mean is, so V lambda, again the weight of lambda is unique here. That is the whole point. I mean, what I mean is, sub lambda, the dimension is 1. This is very important, of course. This is very important. So, here it is strictly less than. Yeah, of course, otherwise, yeah, right. Okay, so, we have another half an hour. Okay. So, now, example of so example, this example. H. This example, here the C of H upper W is to En. What are these notations? Yeah. So, I take for a fixed R between to N, I take all subsets of cardinality R on those indices I take the product. These are all of course polynomial functions. R equal to 2 T n, because r equal to 1 is 0 here, because this is simply the sum and that is 0 here. So, that is why I start from that is why I go from 2 T n. Now, it is clear that the dimension of this is n minus 1, this dimension is n minus 1, and here also you have n minus 1 polynomials are there. So, to prove that this is a polynomial algebra, it is sufficient to prove that this generate, because then it forces that they have to be algebraically independent, as the dimension is because it is a finite group and the dimension will not come down by finite group variance. So, yeah, this part I do not prove it now. Maybe if we need in the tutorial we can do it. Okay, I think yeah, for this theorem I think I went fast. So, can I start with a little bit on the universal algebra and Poincare-Bicot basis to use Harichandra's thing. Okay, then next time I will try to. I thought this will take time to prove it, but okay. Okay, the first thing is that there is a lemma. Alpha is a simple root. Alpha I. Lambda is a non-negative integer, it is a non-negative integer, and okay, and let the lambda so the C lambda is one dimensional representation for B, and I induced to UG. Anupam Singh, I think he talked about this. It's a maximal standard cyclic model. It's a Fermat model. So, there is a unique up to non-zero scalar. Sorry, the lemma is different. I just want to say something before getting into the lemma. Okay, just I say something before getting into the lemma. Okay, it's a unique up to non-zero scalar in lambda. It's a unique vector V plus lambda such that for all x in H and 0 for all simple root alpha I, for all simple root alpha I. Of course, it is known that for all positive roots also it is clear, because they generate the now I state this lemma. So, just so far I have just recall what is the meaning of maximal, I mean one maximal standard cyclic module with maximal thing lambda. Now, lambda be in, I could even assume it's a integral, right. Possibly I do not need integral only for that alpha, I think, not very sure. Okay. So, lambda, the lambda of h alpha I or h I. So, this is equal to m non-negative integer. Suppose this happens, non-negative integer, this is non-negative. Okay. Then y alpha I to the power m plus 1 v lambda plus is a maximal vector in L lambda of weight lambda minus m plus 1 minus alpha I, that for that simple root alpha I. Okay. I just give a sketch of the proof of this lemma. So, maximal means for every, so that has been already discussed, I think. Maximal, meaning of a maximal vector of some weight means for every simple root x alpha I should kill it, x alpha I of that that is 0, and for every element in the Cartan subalgebra that acts through a eigen value, and that value is called this weight. Okay. So, now clearly, I mean, this is clear that, I mean, is minus alpha I of h y alpha I. You have to use this, and of course, h again thing is lambda of h. This what these are the two things that you need to use to get this thing. Now, this to see that is a maximal, to see v lambda plus is maximal firstly, all those relations Anupam wrote on that day completely in connection between the dominant integral weights and the bijection and v lambda is finite dimensional and every weight is of the form mu less than or equal to lambda, and the multiplicity of w lambda is same as w mu is same as mu, everything. So, in that several steps he did, and there he also wrote some, there is a lemma set relations, okay, those things he wrote, and I think one of the relations is that this is x alpha I, y alpha j, and possibly any number also, 0 if I not equal to j. This one I mean the Lie bracket is in the universal looping algebra. The Lie bracket is in the universal because power is there. I not equal to j. The reason being alpha I minus alpha j is not a root. In any root is either a completely a non-negative integral linear combination of simple roots or completely a non-positive linear combination of simple roots. There is no mixer. That is why alpha I minus alpha j will not come. Therefore, it is 0. But we cannot do the same thing for I equal to j. So, there is a little trick there. So, this I think that alpha a power k plus 1, for some reason I write, maybe I will write in a different order. Power k, and then there is this k into 1 minus h I, is that correct? Oh, here there is a minus k plus 1 here. Huh? Here there is a minus k plus 1. Fine, okay. Okay, for me it is not important. I mean, what I mean is for this purpose it is not important. That is why I ignore that k plus 1. I am not okay. Yeah, but in general it is very important. You should write this minus k plus 1 into that. Probably that is why that factorial will come, k plus 1 factorial. That is why the Poincare basis you have this k plus 1 factorial this thing. Okay, anyway, but for my purpose this number is not going to play a role because now h yeah, now I want to say that this so now the claim is the following. Alpha j x alpha j y alpha power plus 1 lambda plus is 0 for j not equal to I, and x alpha I y alpha power plus 1 lambda plus is 0. Okay, I mean I separate the case. I could write even for every j, but then the one implies the first thing, changing I and j. Of course, I have to be very precise. Changing I and j, one implies the first. And this one, the second one, you use this, but okay, let me, therefore, the non-trivial case is only the second one. This is of V lambda plus is by this thing x alpha I y alpha I to the power k plus 1 by m plus 1 and plus so this is equal to, yeah, I want this one only. So, this is that minus plus this one. So, which is plus y alpha I power m plus 1 times x alpha I v lambda plus. But you see, this is already a maximal vector, so this is 0. This is already a maximal vector, so this is 0. But this part times, of course, v lambda plus. But now consider this part. I do it here. Okay. So, this is x alpha I, this thing, by minus m plus 1 y alpha I to the power m into 1 minus h I v lambda plus. But here, this I could ignore, this I could ignore. If this is 0, I can ignore everything. Okay. But this is simply lambda of h I, this is simply a scalar, but lambda of h I is the scalar m. That is what I have. So, therefore, that is also 0. So, this is also 0. So, now we have proved that this is a maximal vector. Yeah? And yeah. I just say one thing about one thing about the center of the universal enveloping algebra and then stop there. So, this part will be used to prove some kind of connection between to see the Harishchandra's theorem that we need this one. So, now we have the UG, the universal enveloping algebra. Of G, and then the you have somehow suddenly I was keep on using epsilon. Then I realized the notation was the other side, but does not matter, you keep following this. If I keep writing again also I may come to epsilon. So, let me. So, this is the center of UG. So, center of UG is that thing. Now, here we consider this Z lambda. That is the representation for UG, and now let Z be in the center of thing. So, this is by definition all those elements G such that Z x equal to 0 for all x in UG center. So, now here Z times v lambda plus, so this is v lambda plus is a maximal vector of lambda. So, maximal vector of weight lambda, same weight. I mean, here I do not need any integral or dominant or anything, any linear form. Okay. So, how do you see that? Just to see that, okay, this is small lemma or observation that for every. So, how to see that? So, now look at H. So, x is a point in H, and what is x times z times v lambda plus? So, this is x z plus z x times lambda plus, but this is 0 because it is in the center. So, this is same as z times, but then x is in H, therefore, it is lambda of H v lambda plus, which is same as lambda of H z v lambda plus. So, therefore, this vector is z v lambda plus is a weight vector for H. I have checked only that part, okay, only that part. Now, let alpha I be a simple root. Consider x alpha I times z times v lambda plus. Use the same thing here now again. So, this is x alpha I comma z plus z times x alpha I v lambda plus. But this is 0 because z is in the center, but this one is x alpha I on v lambda plus is 0 because v lambda plus is a maximal vector. So, this is 0. So, we have seen that this is a maximal vector. Okay. Just 5 minutes, I introduced the one function from the center to C, and with that we will stop. It will be a finishing. Okay. Just to use this to get that function. Anyway, I will also recall this in the next lecture also, so that we will be very. Now, here consider all those some notations of some z lambda, some okay, some 0, some just some notation which I some notation this or lambda comma epsilon. This is for epsilon. So, now this is all those b in z lambda such that z times v. Okay, just one second. So, here just before that I need one. Since is a maximal vector of weight lambda, we know by the uniqueness of the multiplicity z v lambda plus is some chi lambda of z times v lambda plus. So, for every z, see we have checked for every z in the center, z v lambda plus is again a maximal vector of weight lambda. Okay, so, z v lambda plus is chi lambda of z times v lambda plus. For some chi lambda, which is a homomorphism, of C algebras. So, now we have a homomorphism of C algebras. I just finished with this today, and we will in the next thing we will show that small thing is that in fact, every vector in Z lambda is an eigenvector for epsilon with chi lambda present, not just the maximal vector, every vector. Because the idea, I don't write anything. The idea is because Z is in the center, epsilon is in the center, and this is a cyclic module, and that v lambda plus is already in that way eigenspace for Z, for epsilon. And since some this is a general thing, some center is acting by a scalar, then the entire thing will permute that thing. But then this then that becomes a UG module, because you write any x times, take x times b, then look at z times x is simply x times z. Therefore, that should be the same scalar. So, that is a module. Therefore, that set of all the weight space for chi lambda for epsilon is a UG module. But that UG module contains v lambda plus already, and this is a cyclic module in the sense that generates the module. I mean the v lambda plus, everything in the UG you apply to v lambda plus, you get all vectors. Therefore, it becomes the entire model. Okay, so this this chi lambda of z is the thing for the complete complete thing. So that anyway, I will write out the formal details in the next thing. Yeah.